So let us start. In last class, we have seen nearest neighbor rule to make the classification, and we take the help of nearest neighbors around the test sample to do the classification. So that is the technique. We also found that, or we also noted that this system of classification is erroneous, and its error is in the range, say, base error to twice base error, and it works on the estimation of posterior. It is not calculating likelihood, it is directly calculating the posterior answer. Then we saw the concept of Fahrenheit oscillation. Say, given two samples, how a decision boundary is automatically formed with the help of nearest neighbor. Say, here only one neighbor is considered. So if this is the prototype given to us, say belonging to class 1, and this is prototype for class 2, then this decision boundary is formed automatically because of nearest neighbor. Then we have seen, if I take many such samples, many such prototypes belonging to, say, two classes, then how decision boundary is constructed. So you can see these boundaries in total are forming a nonlinear decision surface, and that's why these methods are very popular. So if I take say more complicated example like this 3D or the 2D with many samples mixed together belonging to two different classes, then you can see the boundary for, say, white class is like this. It's very complicated, and this portion of class 2 is submerged in class 1 here. Okay, so again there is class 1 boundary or class 1 region, and again there is, say, class 2. So anything is possible, a complicated thing is possible with the help of KNN. Then we saw the importance of metric, how we measure the distance between two samples, because KNN directly deals with distance between X test and its neighbors. Okay, and the way of measuring distance between 2 points is not just Euclidean way. There are many ways of doing it. So generalized way of doing it is called as Minkowski distance that we have seen here. And then we saw if I put k equal to 1 in Minkowski, it will be known as city block distance. Okay, if I put k equal to 2, then it will be our normal Euclidean norm. So we have seen with different values of k how a unit distance we can have, or what are the shapes of this unit distance. So this is very familiar to us. If this is point A and this is point B, and if this is a unit distance, then if I take a point, say B dash here, this also has a unit distance. So if I choose, in fact, any point on this circumference and join with this center point, its distance is unit. So this is very easily understandable, but You can note that if I take k equal to 1, that is city block, and if this is point A and this is point B, this distance and this distance, so this B, the distance between AB and distance between AB dash is same as far as city block is concerned. Similarly, if this is A and this is B, if this is B dash, these two distances are same if it is k equal to infinite. Okay, so like that, it depends on the measure, how you measure the distance between 2 points, what formula you are using, that will be defining your neighborhoods. Okay, so depending on the problem, depending on the other factors, you have to choose the proper value of k which suits your problem. Then we saw one example. A table was given to us. So these are samples given to us in the form of a data table, and these are labels associated with it. And question was, if I want to classify X test is equal to 3 comma 2, what is class? So what we did, we you can see the scatter plot of these samples. So there are actually three groups, say omega 1 here, maybe omega 2 here, omega 3 here. Then what we do is we just take that 3, 2 and find out distance with each of these given training prototypes, and then arrange these points according to their distances. So here I am using k equal to 2, that is Euclidean norm in our Minkowski formula. Okay, so from minimum to maximum, I am arranging or sorting these samples. So minimum distance from 3 to with 3.5, that is this first entry in this table, and 3.5 comma 1 is 1.12. So this is minimum and this is the maximum. So accordingly we have arranged, and then we take the k nearest neighbor equal to 3, suppose. Then we take first three uh, prototypes into account and check which class is holding the majority. Now suppose I put here k equal to 5. So this table will not change. Only thing is that I will consider up to this point. So these 5 samples are considered. Then I will see which class is the majority. So again here I can see 1, 2, 3. These are 3 prototypes belonging to class 3, and there are 2 prototypes which belong to class 2. So majority is class 3. So my decision is class 3. Okay. So like that I can keep on increasing value of k, maybe k equal to 11 and so on. Then I need to consider up to this point and take a decision. So basically, theoretically, we can say that if you increase number of k, then your decision is more stable and you will not be moving away due to the noisy samples around the test sample. Okay, you can take a firm decision by asking many people around that sample that what is your label. Then we have seen a modified version of this KNN, which takes into account not only the neighbors but their distance from X test. So for example, this is my X test, and say by chance I have these 2 samples as my neighbors, and maybe these 2 samples as my neighbors, or maybe 3 samples as my numbers. If I choose suppose k equal to 5, then this is the situation. So majority is with this class, but you see that these two samples are actually close to this. But if you use the earlier KNN, that is the plain KNN or vanilla KNN, which just takes into account k equal to 5 samples around u, then it sees that okay, this is 3 and this is 2, then declare class 3, which looks odd to us because we know that this X test is more close towards these two samples. Okay, so what we do is we take into account distance here between X test and the prototypes to take the decision. So same problem we have solved using uh, distance in taken into account. So suppose I say k equal to 5, then these yellow mark sorted distance samples are taken into account, and we find out the importance of each prototype. So this is 3-5 prototype. Its importance is 1 because it is closest to the X test. Okay. Then we find that say this is 4-1, which is the far away sample from X test. We put its weightage equal to 0. So as per the formula, that is d max minus dj divided by d max minus d mean. So actually we are weighing with respect to this maximum minus minimum distance. So if it is dj is equal to d max, then this will be 0. So you will get minimum weightage, that is 0. If dj is equal to d min, then you will get maximum weightage. Now what we do, we just then split this weights according to their class labels and then sum. Okay, so whichever sum is more, then we decide that class. You can see this previous example here. Since these two samples are very close to X test, their weightage, say W1 plus W2, will be more than the weightage for these, say W3, W5, and W6 samples. Okay. So these weights, if you add together, will be obviously less than this because they are close, and then we can take a better decision. So that's why this modified KNN is proposed. But obviously, when you have more accuracy or when you have more advantages, then you have a disadvantage of more calculations. So you have to have more calculations to take this kind of decision using modified KNN. Okay, so this was the you can say this is the end of non-parametric training concepts. So we will move on now to the next point. Just 1 second. The next point is decision tree classifiers. So we have this new topic now. Again, this is used for classification, and the thing is that we will try to construct decision trees and we will do the job of classification. Now the decision tree is looking like this. We have some nodes here. So this is the parent node, and these are some children nodes. Okay, and at every node there is some decision taken. Once you take that decision, then you move to the next node, then you take a decision, then you move to next node. Like that you will proceed, and then you finally land to this leaf node. Okay. So all these are branches, and this is a leaf node where final classification will be done. So these are class levels. So decision tree is most popular data structure used in classification or pattern classification. It consists of leaf and non-leaf or branches or internal nodes. So you have leaf node here, and these are all internal nodes. Leaf nodes correspond to the class decision, and a decision tree are used for classification where each path is a set of decisions leading to one class. So you take any path, you will see in detail. Say if I take this path with some decision uh, criteria, then I move to this side because of the decision taken at this point, and then I move to say this side because of some condition here. So I have a path, say like this, to take this final decision. So this particular path is forming a rule to classify given input into this group or category. So if I say at this point I have not satisfied this side, then I will move to this side. Then suppose I take this decision, and then I take this decision, so I will land this class. So like that, at each node you have to take certain decision. Path from the root node to leaf node represents a set of rules which leads to classification. So this is called as root node. This is internal node, and these are leaf nodes. Designing a decision tree needs a variable to be used for splitting at each node is to be determined. That means for uh, designing such kind of decision tree, we have to take the help of features. So we have feature vectors for given to us for a given problem, and at each node we are going to take the help of those features, one of the features, so that we can take a decision to go this side of the tree or this side of this tree. These links are mutually exclusive but collectively exhaustive. Meaning is what? So if I take a link, suppose this is my path, there is another path, there is another path here. So there are so many paths that are running as per the number of actual classes. Then I can have this path, I can have this path. So there are, say in this diagram, 8 paths. Okay, so 8 paths are mutually exclusive. That means they are not overlapping with each other. Okay, so mutually exclusive and collectively exhaustive. So they will exhaust all the possibilities if you consider all of them. Okay, so it's like a set, say A and B, they are mutually exclusive. They are not overlapping with each other, but when you consider A and B, they are exhaustive. So they are fully occupying all the space. So that is what this line means. It is fully mutually exclusive and fully exhaustive. In a path, a node with same label is never repeated. So that thing you should keep in mind. In a path, a node with same label is never repeated. A decision tree is not unique, as different ordering of internal nodes can give different decision trees. So it's not like that only one tree you will get for a given problem. You can have different structures of trees, and it, they may solve your problem. So there is no unique, there may not be a unique solution. Internal these nodes, if you change their orders, then your tree will look different. Now let us take one example of a binary decision tree. This is a binary decision tree. At each node, why it is called binary? Because at each node I take a decision yes or no. Okay. Now suppose I have three variables A, B, C, and I take all the possible binary values. So 0 and 1 each variable A, B, C. So there are, there are 8 combinations. So 2 to the power 3. And I call this combination say 0, 0, 0 as say M0 or omega 0, and then this is class 1, 2, 3, and so on up to 7. Now, based on this, I want to make a binary decision tree. So if I am given a combination, suppose 0, 1, 0 or ABC, then we have to tell what is class for this. So we can make a decision tree. Suppose I put the node A, that is variable A, as a root of this problem. Okay, so this is my choice. You can have your own choice. Then I have said that each node has to take a decision yes or no. So here suppose yes means 1 and say yes is 1 and no is 0. Suppose I take a decision yes. So that means I'm moving in this direction, that is A is equal to 1. So you can see this table, A is equal to 1 is here. Then I have internal node B. I put this internal node B and check the value of B. If it is 1, then I will move this side. Okay, so you can see here, if this is 1, this is 1, that is B is 1, I have now two options. It can be with C equal to 0 or it can be with C equal to 1. So given B is 1, A is 1, C is 1, then everybody is 1. So my class is M7. If this C is 0, then I will move this side. Then my class is M6. Okay, so if I choose this particular path, that is A equal to 0, B equal to 1, C equal to 1, then the resultant category or class is M7. So what is my rule implemented in this first branch here is if A is equal to 0 and B is equal to 1 and C is equal to 1, then class is equal to M7. Now let us randomly choose, say, this path. Now what this path is implementing, it is saying if A is equal to, so this has to be 1. Sorry. If A is equal to 0 and B is equal to 1 and C is equal to 1, then class is equal to M3. Okay, so thing is that if you choose any path, it will give you one implementation of one rule. So here, if I take this branch, then it is saying A equal to 0 and B equal to 0 and say C equal to 0, then M is 0, that is class is 0. So I am implementing this rule here. Okay, so look, I hope you got the idea of a binary tree. So same idea can be extended with numerical values. Now here, this is a good example to understand. Now suppose we are given 3 coins A, B, C, D, sorry, 4 coins A, B, C, D, and 3 of them are common coins and they weigh equal, and 1 coin is heavier. So which one we don't know, and question is find the heavier coin. So there are four coins, 3 are same and 1 is different, but they are mixed and we don't know which one is heavier. Now to find out which one is heavier, we can have a decision tree as shown. So what I do, I just call 4 coins as A, B, C, D. Then I take any 2 coins, say A and B, and then I take another 2 coins, C and D, and weigh them at a time. Now, question arises here, if A plus B is greater than C plus D, then you go to this side. Otherwise, you will go to this side. Okay. Now, suppose A plus B is more than C plus D, then you check whether A is greater than B. Then you say straightway A is the heavier amongst 3. Otherwise, you will declare B as the heavier coin. Now, if A plus B is less than C plus D, then you will travel this side. Now, here, since C plus D is greater than A plus B, you just check now whether C is greater than D. Yes, then this is heavier coin. Otherwise, this is the heavier coin. So what we have done is we have 4 nodes corresponding to our possible outcomes. So there are 4 leaf nodes here. I should call them leaf nodes, 2 internal nodes, and 1 root node. So this is root node, this is internal node, and these are leaf nodes. Now it requires only weighing, only 2 weighings. Okay, so I need to do weighing 2 times only to take the decision, not 4 times. I can solve this problem if I take each coin independently and weigh it, and that is also possible. But when I do this way, I require only two measurements. Okay, and I can directly come to the conclusion. And you can see each path again is corresponding to one rule. So suppose I take any path, suppose I choose say this path, then what is rule implemented here? If A plus B is greater than C plus D and A is greater than B, so the answer is no, then what we have to see, we have to say is, and I have to apply now not here operator, A greater than B, then outcome is B. So B is the heavier one amongst three. Okay, so remember we are deciding amongst three actually, but with the help of only two measurements. So we can try with some other paths like this. So if A plus B is actually less than C plus D, and say not, or I can say C is less than D, then outcome is D. We can form four rules for each leaf node in this structure. Okay, so it's very simple. You have to just see the facts from given table and then try to implement. So this is a table-based method for learning. So how do I do the internal node calculation, or what is to be tested at the internal node? In a decision tree, each internal node in the decision tree is associated with a test based on one or more features. But these tests are grouped as axis parallel test. That is, the test is of the form x greater than some threshold or greater than equal to some threshold. Now suppose I have this spread of data. So this is some class 1 and this is some class 2. Then I can say that upper side of this line is class 1 and lower side of this line is class 2. So for doing this, I just implemented one condition, that is y is greater than theta, and say this is y equal to theta line. Now this line is parallel to this x-axis, so that's why the axis parallel name is given to this. Now in some other case, I can solve the problem with say x less than theta this side. I should actually say x greater than theta this side and x less than theta this side of the line. So this line is implementing some x equal to theta. So when I consider say one node and here I say check if x is greater than theta. That means I am checking based on only one feature. I am not considering y feature, so I am ignoring it. That means I am implementing this line at this location of that node, and if this is greater than theta, yes, go this side. That means we are entering into this domain. Otherwise, we are entering into this domain. Then we can have further checking of some other feature. Okay, so here you try to understand that this at this node we are considering only x feature. We are not considering y feature. Suppose I have x, y, z, and suppose some z dash as my 4 features. So at each node, basically I am considering only say one feature, maybe at random, but I am considering one feature at a time. That means I am implementing axis parallel test at each node. Now this axis parallel test may not be sufficient since such kind of data that is shown here you cannot solve with such kinds of line. Okay, so I just check, so I just put some y equal to theta line here or x equal to some theta line here, then there is a lot of misclassification because of this such kind of decision nodes. So the best way to solve this is to put this kind of line. Okay, so if I'm able to put this kind of line, then it will be properly classifying two groups into two classes. That is, this side is class 1 or this side is class 2. So that is possible. Now to implement this kind of a thing at a node, I cannot just rely on say x or y. I have to take into account both x and y. That means I have to take into account this line equation. So this line equation I can write as suppose a1x plus say b1y equal to 0, or as a standard form I can write for n dimensional as the w1x1 plus w2x2 plus w3x3 plus and so on up to wn xn. So if it is greater than some threshold, so this side, then I am omega 1, or less than that I am omega 2. So at the node location I have to take into account many features. If I'm able to do that, then I can directly use such kinds of line at that node. But if I'm considering only one feature at a time, then I am using this axis parallel technique. Okay, so that may be leading to some errors. Now the third way is the most generalized way, is called as non-linear combination. That means if this is the spread of your data on xy plane, then a straight line is not even not sufficient to classify all the samples correctly. Suppose I even put this tilted line as per the previous discussion, these two things are going to be misclassified. So to properly classify, I need this kind of a curve. This is a non-linear curve so that the results are perfect. Now this is some f of say x, and if it is more than some theta, then I will say this is class 1, otherwise this is class 2. So this is the most generalized way, but computationally it is most expensive way of doing it. So we will see maybe first or second way of doing this. So we will take this example in next class, how to solve or how to make a decision tree for such kinds of tables. Okay, so let us stop here.